In this video, we'll explore further information about trig graphs. We'll look at an applied setting in biology using sign graphs. We'll use information about the domain of trig functions to determine a new domain after we've translated a function. And finally, we'll look at sketching the graph of a trig function given an equation and several translations. One of the uses of trig functions is to model real-life data, as it often mimics the sort of natural rhythmic flow of sinusoidal graphs. In this problem, the number of Norway's wolves, also known as Canis lupus, are managed and limited to particular wolf zones. Yet this number can vary over time because of the amount of available resources and conservation efforts. If the number of wolves were determined by the function y equals 15 sine of pi t over 2 plus 30, where t is in years, then what are the highest and lowest number of wolves in any given zone, and how long is this cycle? So first let's address, well, what is the highest, the maximum, and the lowest number of wolves in any given zone? So if I have my function y equals 15 sine of pi t over 2 plus 30, well, one thing I know is that sine of pi t over 2, sine is always bound between -1 and 1. So regardless of what the t is, this value will range between -1 and 1. So I know then that if it's at -1, that's going to be the minimum value that it obtains. So my y minimum will occur when we have 15 times -1 plus 30. So -15 plus 30 is 15. So the minimum number will be 15 wolves. And the maximum number will occur when sine is 1. So 15 times 1 plus 30 equals 45. So we know the wolves are going to range between 15 and 45 in any given zone. And now I want to determine, well, how long is that cycle? Well, I know information about the period, so the period will be how long that cycle is. And that's always given by 2 pi divided by whatever the number is equals the period. That's if I have something along the lines of sine times bx. So in our instance here we have pi t over 2, so my b value is pi over 2. So my period will be 2 pi divided by b, which is pi over 2. So that equals 5. Multiplied by the reciprocal, it's 4, equals the period. And that information was in years. So every 4 years I'll have this cycle. Between 15 and 45 wolves every 4 years will be this conservation of low and high numbers of wolves. In the following problem, we need to find the domain for the function y equals cosecant of 2x plus pi over 2, where we've taken our cosecant graph and we've translated it and changed the period. So let's use information that we know about our cosecant graph is really 1 over sine of 2x plus pi over 2. The domain for this function is all values where sine of 2x plus pi over 2 doesn't equal 0. So sine of 2x plus pi over 2 doesn't equal 0. Because if this is 0, then we can't divide. So now, what are the values of sine what values of angles will make sine be 0? Well, that occurs at all multiples of pi. So any n pi is where this expression here would evaluate to 0. So we know that that can't equal 2x plus pi over 2. And now I can solve for x and say, okay, well that means 2x can't equal some multiple of pi shifting by pi over 2. So that means any x that I use can't equal n pi divided by 2 minus pi over 4. So any multiple of pi over 2 shifted by pi over 4 will not be in the domain of this function. Here we have the equation of a sine function, and I want to determine its graph. So oftentimes what we'll want to do is get this in the form y equals a sine of b x plus c plus d, because that'll give me information about the amplitude, the period, a horizontal and a vertical shift. So if I rewrite this expression now, I have y equals -1 times sine b. Well, I could factor out the 1/2, so then I have x plus pi, 2 pi here, plus 3. So I know that it's horizontally shifted to the left. So here I have a left shift by 2 pi units and a vertical shift up for 3 units. Now the period, 1/2, I know that 2 pi divided by b will be equal to period. So 2 pi divided by 1/2, that equals 4 pi. So my period is 4 pi. And this -1 means that my sine graph is now reflected about where it's centered. So we know that it's shifted up 3 units. So normally what I would do is I would start my sine function here at the origin, but that's going to be shifted over to the left 2 pi units, so 1, 2, so this is -2 pi, this is -pi, and it's going to be shifted up 1, 2, 3 units. So my sine graph is going to have a value right there at -2 pi, 3. And typically we'd expect that my sine graph would go up like this, do something like that. But instead it's going to be reversed, and so we'll just consider that. Well, I know that the period, pi, 2 pi, is 4 pi. So it'll make one full oscillation between -2 pi and 2 pi. So I know that there'll be value here as well. And because it's a sine graph, I'll have a point there at +3. So I know it's going to look something like this, where I'll have a minimum value because it's sine occurring at -pi, halfway in between these 2 points. And the amplitude is 1, so that'll occur at the value of y being 2, 3. And then there'll be a point here at the value of 4. So now I can do a sketch of what this is going to look like. My sine graph is going to look something like this. It's going to continue. But this should make sense because it's the period from here to here is 4 pi. Its amplitude is 1. It's shifted to the left by 2 pi units and vertically shifted up so that it's centered here at y equals 3.